Welcome to Algebra. Today, we are diving into the fascinating world of symmetric and skew-symmetric determinants. Imagine folding a grid of numbers like a piece of paper. How those numbers align can reveal incredible shortcuts for solving massive complex equations instantly without doing any heavy calculation. Let us explore exactly how this mathematical magic works. Before we fold any grids, we first need to understand what a matrix is and why it is so useful. A matrix is simply a rectangular grid of numbers used to organize complex data in linear algebra. If we take this grid and swap all of its rows with its columns, we create a brand new grid. Mathematicians call this new grid the transpose, and we write it as A superscript T. This simple swapping action is the absolute foundation for understanding symmetry and how matrices transform space. Now that we understand the transpose, let us look at how it defines symmetry in a mathematical sense. A matrix is called symmetric if swapping its rows and columns changes absolutely nothing. The original matrix and its transpose are perfectly identical. Conversely, a matrix is skew-symmetric if swapping its rows and columns produces the exact negative of the original matrix. Physically, symmetric matrices represent stable, stretching forces in a system, while skew-symmetric matrices represent rotating forces that do not stretch space in straight lines. To truly grasp this concept, let us visualize the folding analogy we discussed earlier. On the left side of the diagram, notice how the symmetric matrix has identical values reflecting perfectly across the main diagonal. It is a perfect mirror image. On the right side, the skew-symmetric matrix has opposite values reflecting across a diagonal that is made entirely of zeros. This visual structure is exactly what forces their determinants to behave in such strict, predictable ways when we calculate them. With the visual structure clear, we can introduce the determinant. The determinant is a single number calculated from a square matrix that tells us how much that matrix stretches or shrinks geometric space. Beyond just the determinant, these matrices have profound implications for their eigenvalues, which are special stretch factors. For a symmetric matrix, the eigenvalues are always purely real numbers. For a skew-symmetric matrix, the eigenvalues are always purely imaginary numbers or exactly zero, which perfectly matches their rotational nature. This brings us to one of the most famous and useful rules in algebra. If you have a skew-symmetric matrix with an odd number of rows and columns, its determinant is always exactly zero. Conceptually, this means any odd-sized skew-symmetric matrix completely flattens geometric space into a lower dimension. You know this instantly without looking at a single number inside the grid. Let us see what changes physically. As the matrix size increases, as long as the variable n remains an odd number, the scaling volume will always collapse to zero. Before we prove why this happens, let us verify our theorem by calculating the determinant of a specific 3x3 skew-symmetric matrix. We are given a matrix where the main diagonal is all zeros and the mirrored elements are exact negatives of each other. We want to find its determinant to see if it truly equals zero. We will use the standard method of expanding the determinant along the first row, which contains the numbers 0, 2, and -3. This will test our rule perfectly. Continuing our expansion, we multiply each element of the first row by the determinant of the smaller 2x2 matrix that remains when you cross out that element's row and column. Remember to alternate the signs for each term as you move across the row. The first term is multiplied by 0, so it vanishes completely from our equation. For the second and third terms, we need to calculate the determinants of the smaller matrices by cross-multiplying their diagonals and subtracting the results. Simplifying the arithmetic inside the parentheses, the first inner calculation becomes 0 minus 12, and the second inner calculation becomes 8 minus 0. Multiplying these values out, we get positive 24 for the first part and negative 24 for the second part. Subtracting these gives us our final answer of 0. Just as our theorem predicted, the determinant is exactly 0, confirming physically that the matrix flattens three-dimensional space into a lower dimension without any residual volume. Now that we have successfully used this rule in a concrete example, let us understand where it comes from by proving it mathematically. We start with the fundamental definition of a skew-symmetric matrix, which states that the transpose of the matrix A is equal to the negative version of the matrix A. Next, we want to find the scaling factor, so we take the determinant of both sides of this equation. This sets up our derivation perfectly. By establishing this initial equality, we create a bridge between the structural symmetry of the matrix and its geometric volume, which will allow us to uncover why the determinant must vanish. Moving forward with our proof, there is a universal rule in algebra that the determinant of a transpose is always equal to the determinant of the original matrix. So the left side simply becomes the determinant of A. Now we must deal with the negative sign on the right side. When we pull a negative sign out of a matrix with n rows, we cannot just pull out one negative sign. We must pull out a negative one for every single row in the grid. Therefore, we multiply negative 1 by itself n times. This algebraic step is crucial because it links the size of the matrix directly to the sign of its determinant. Bringing it all together, if n is an odd number, like 3 or 5, multiplying negative 1 by itself an odd number of times results in negative 1. This leaves us with a fascinating logical statement. The determinant of our matrix is equal to its own negative. In the realm of ordinary numbers, there is only one single number that is equal to its own negative. By adding the determinant to both sides and dividing by 2, we prove our final result. The determinant must be exactly 0. We have now mathematically proven why odd-dimensional rotational forces completely flatten geometric space. This proven rule leads us to an important question. What happens when the matrix has an even number of rows and columns? If n is an even number, the negative signs we pulled out earlier completely cancel each other out. In this case, the determinant does not flatten to 0. Instead, it turns out to always be a perfect square of a polynomial, known as the Pfaffian. Physically, this means an even-order skew-symmetric matrix scales space by a squared factor. As the matrix elements increase, the overall volume scales up in perfect squares, maintaining a positive geometric volume. Before we move on to real-world applications, let us see this even-order rule with a concrete example. We are given a 2 by 2 skew-symmetric matrix B and asked to find its determinant. The main diagonal consists of zeros and the off-diagonal elements are 5 and negative 5. According to our earlier discussion, this should result in a perfect square rather than 0. We will use the standard cross-multiplication rule for a 2 by 2 matrix, multiplying the main diagonal and subtracting the product of the other diagonal. Finishing the calculation, we multiply the numbers together. The first part is 0 and the second part is negative 25. Subtracting a negative number is the same as adding a positive number. This gives us our final result of 25. 25 is indeed a perfect square, specifically the square of 5. This perfectly aligns with the mathematical rule that even-order skew-symmetric determinants always yield perfect squares. Physically, this confirms that our two-dimensional rotational system scales the area by a factor of 25. Now that we have used these formulas, why does all of this matter in the real world? In quantum mechanics, symmetric matrices are used to represent observable physical quantities like the energy of an electron. Because their eigenvalues are always real numbers, we are guaranteed to measure real energy values. On the other hand, skew-symmetric matrices are heavily used in electromagnetism to represent magnetic fields. Knowing that a 3 by 3 matrix has a determinant of 0 can instantly simplify massive equations, saving immense computational time and preventing catastrophic errors in simulation software. To summarize our journey today, the mirror-like properties of these matrices dictate their entire mathematical behavior. Symmetric matrices remain unchanged when swapped, leading to real eigenvalues and orthogonal eigenvectors. Skew-symmetric matrices become their own negatives, guaranteeing that any odd-sized matrix has a determinant of exactly 0, while even-sized ones yield perfect squares. Mastering these rules allows you to bypass tedious calculations and immediately understand the physical properties of the systems they represent. You have now successfully covered the full topic of symmetric and skew-symmetric determinants.